for this problem, we are looking at finding the definite integral, but we're going to use the Riemann sum approach to do this. Let me change my color to blue. There we go. And the interval we're using is 0 to 9, so that just tells us our delta x is going to be 9 minus 0 over n, because it's n intervals, so 9 over n. And we're going to be using the right endpoints for each c sub k. So that's going to be c sub k equals 0 plus 9 over n times k. So we have, that's just going to be 9 over nk. Now, because it's the right interval, right end of the intervals, just think about the intervals 1, 2, and so on. We want the right end of the interval, so we'll start with our k being 1 when we do this. So it doesn't make a big difference if we did k at 0, but we'll go with k starts at 1, and that'll help us to come up with the formula probably a little bit easier. Okay, so what we're looking at is it's an infinite limit, and let me just say this for those who are stressed out about doing this process. We don't do this process forever. This is like how we did the long way to get the derivative. This is the long way to get the integral, and then we learn the shortcut techniques, and we do that from that point on. So we're going to take the limit as n goes to infinity of the sum k equals 1 to n. Again, we started at 1 because it's the right end of the interval, of f of c sub k delta x. So that's our basic formula. Now we're going to fill some pieces in. So that's going to give us the limit as n goes to infinity of the sum as k goes from 1 to n of f of, that was 9k over n basically. That's our c sub k, and then our delta x is 9 over n. So if we put some numbers in here, we have the limit as n goes to infinity of the sum as k goes from 1 to n of our function is 81 minus x squared. So it's going to be 81 minus, instead of x squared, we have 9k over n, and that expression is going to get squared, times our delta x, which is 9 over n. So we'll end up with the limit as n goes to infinity of the sum as k goes from 1 to n of 81 minus 81k squared over n squared times 9 over n. So by the way, this summation here is going to affect things with the k. The only thing with the k is right there, but that whole expression here in the parentheses will have to stay there. But this 9 over n can be treated as a coefficient to this whole summation, so I can take this and put it out front here as I will in the next step. So we have the limit as n goes to infinity of 9 over n of the sum. I'm going to split this up. K goes from 1 to n of 81, put a big bracket here, minus the sum as k goes from 1 to n of 81k squared over n squared. Okay, now we're starting to get somewhere with this. So we have the limit down there further. Okay, the limit as n goes to infinity, 9 over n. Now if we added 81 n times, 1, 2, 3, 4, until we get to n, that's going to be 81n minus, now the second part, so notice 81 and the n squared, they're not affected by k, so they can become coefficients to the summation. So we have 81 over n squared times the sum, as k goes from 1 to n, of k squared. Now, this part, there are the special formulas you probably read in the book. And an infinite sum for a k squared, that's what we're going to substitute in now and get rid of this summation. We have the limit as n goes to infinity of 9 over n times 81n minus 81n squared over n squared, times, and this sum, infinite, or not infinite sum, the sum, as k goes from 1 to n of k squared, is n times n plus 1 times 2n plus 1, all divided by 6. Okay, now we're going to have the limit as n goes to infinity of 9 over n times this 81n, I'm going to distribute that now, minus 9 over n times 81 over n squared times, and this n times n plus 1 times 2n plus 1 is 2n cubed plus 3n squared plus n all over 6. And I still need to have some kind of a way to keep this all within this limit. So now we can take this, let's do a little bit of algebra here, and I'm going to do some canceling and simplifying. We'll do this a few times. Right here, this n can be divided with the n down to the denominator. Then 9 times 81 is going to give us a 729. Okay. And this 9, that doesn't matter which one we go with, the 9 and the 6, we can reduce a 3 out, so that's 3 and 2. So now where are we? We have the limit as n goes to infinity of 729 minus 3 times 81 is 243 over n cubed, that's n times n squared is n cubed, times 2n cubed plus 3n squared plus n. Okay, let me scroll this up a little bit. Give myself some more working space. We're getting there though, we're close, so don't lose heart. So the limit as n goes to infinity of this 729 minus the limit as n goes to infinity of, we have 243 over n cubed times 2n, I forgot the 2 down below, put the 2 there, 2n cubed plus 243, in fact I'll split that out too. Let's do a bunch of different little limits. The limit as n goes to infinity of 243 over 2n cubed times 3n squared plus the limit as n goes to infinity of 243 over 2n cubed times n. Now if we look at these individually, we have this first one is just our 729. We have minus what? This n cubed cancels with the n cubed there. This 2 cancels with the 2 there. What's left is just this 243. So minus 243. Then if we look at it, this n squared would reduce out with the n cubed, leaving an n down below. So as n goes to infinity, this goes to infinity in the denominator. making this expression here into a 0. And then here this n reduces with the n cubed, makes it an n squared. And this denominator goes to to infinity, which makes the fraction go to 0, so plus 0. So the result of this is 729 minus 243, which is, drumroll, 486. And that's the answer. Back up here, 486. Okay, hope that helps.